Hello and welcome to York Observatory's weekly Teletube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Allen Carswell Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts most Wednesday nights at 7:30 p.m. local Toronto time at www.youtube.com/user/YorkU Observatory/live. For any questions or comments that you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle @York Observatory and on Facebook at Allen I. Carswell Obs. We'd like to inform you about the Summer 2023 Astronomer in Residence program. This program is a collaboration of the Allen I. Carswell Observatory with Killarney Provincial Park to host astronomers in the certified dark sky site of Killarney to lead in-person presentations and shows using the park's observatory. Julie Tomei, who for over 20 years has inspired wonder and curiosity about the night sky through her work at various observatories, science centers, and museums, as well as through numerous outreach activities and the York Universe radio program, was the fourth 2023 astronomer in residence to have arrived at Killarney Park recently on August 14th. In addition, Raj Sihra, a fourth-year undergraduate student pursuing a degree in astrophysics at the University of Manitoba, was the fifth 2023 astronomer in residence to have arrived at Killarney Park recently on August 21st. If you are at Killarney Park, make sure to stop by at the observatory and say hi. In the meantime, their blogs can be found on www.yorku.ca/science/observatory/AIR/astronomer-in-residence-blog. Good evening, everyone. I'm Sergiy, and I'm joined by Ren, Marianna, Maheen, and of course our esteemed guest this evening, Ricardo Lewis Lambo. And we're here from the Allen Carswell Observatory at York University. Tonight, we've got a great presentation about entropic gravity by our guest, Ricardo Lewis Lambo, who will be shortly introduced by Maheen. The observatory at your campus is in Toronto, and we would like to welcome you all to our show and acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Toronto has been taken care of by the Anishinaabe Nation, the Haudenosaunee Confederacy, the Huron-Wendat, and the Métis. It is now home to many Indigenous peoples. We acknowledge the current treaty holders, the Mississaugas of Credit First Nation. Our stargazing and astronomical efforts during the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in the area.
Welcome, everyone. Before we get started with our main show, we want to give you a little update on what you can see this coming week in Ontario. The moon is in the waning crescent phase with an illumination of 42.41% as seen from Earth. This is the phase where the illumination of the moon will increase each day until it reaches 50%, also known as the first quarter phase, meaning in this phase, the moon will go from 0% to 50%. We are heading towards a full moon that will occur on August 31st. The waning crescent phase, like all moon phases, will last for just over 7 days. The sunset tonight is at 8:09 p.m. EDT, and there are many objects in the sky to see. The moon will be up tonight above the horizon from around 1 p.m. EDT to just before midnight, along with Saturn and Jupiter. Saturn will be very close to the constellation Aquarius and is close to being in opposition, which means it is the brightest and closest to the Earth it will be all year. Jupiter can be found close to the constellation Aries after 11 p.m. And if those planets aren't enough, Uranus will also be up, found close by Jupiter, and Neptune will be visible close to Saturn. The summer triangle will also be visible. The summer triangle is an astronomical asterism made up of 3 bright stars, Vega, Deneb, and Altair. Other celestial objects such as Arcturus, Antares, Polaris, and many more will be up throughout the night. Most of these objects will be visible to the naked eye on a clear, dark sky. However, the use of binoculars or a telescope for viewing is always encouraged. These objects are super cool and definitely something you do not want to miss, so make sure to get outside and look up at the stars. Now I would like to give it away to Maheen so she can introduce our guest speaker for tonight's Teletube.
Thanks, Ren, for telling us about some wonderful space targets for this week. I would now like to welcome and introduce our guest speaker, Dr. Ricardo Lewis Lambo, for tonight. Ricardo Lewis Lambo completed his PhD from the Federal University of Rio de Janeiro in the year 2010, where he worked for a year on the Alpha collaboration at CERN. The purpose of the collaboration was to make and trap cold antihydrogen made up of a positron and an antiproton. Ricardo became interested in the subject of gravity because Alpha did equivalence principle experiments testing whether anti-atoms fall under gravity at the same acceleration as atoms. He then worked for 10 years in China at the Chinese Academy of Science in Shenzhen and also at the University of Science and Technology in Hefei, Anhui Province, China. He worked further on trapping atoms by matrix isolation spectroscopy, which is a way of getting high densities of cold atoms by condensing them into a transparent solid neon at 4 Kelvin. Ricardo then took up a postdoc at York University on the EDM-Cube collaboration that is using this technique to detect and measure the permanent electric dipole moment of the electron, which would test time symmetry and other aspects of fundamental symmetry. Now, without any further delay, I will now hand it over to our speaker for tonight to tell us all about entropic gravity.
Okay, so thank you very much to Professor Hyde. Thank you very much to the crew at the observatory for giving me the chance to speak. So even though I'm here to impart knowledge, actually while I was preparing this talk, I learned a lot. So before I get to the subject then of entropic gravity, I'm going to just talk about plane gravity to start with. So our common sense understanding of gravity is that it's a universal force of attraction between all matter. And even though it's very commonsensical, it's sort of surprising how long it took humanity to arrive at this understanding. So the very first understanding then of gravity as a force comes from 7th century India, particularly astronomers sort of like Brahmagupta. He was one of the first persons to write, all things fall down to earth by a law of nature. And not only him, but his contemporaries sort of compared earth being held sort of like a piece of iron by a magnet. So they had a sort of vague understanding of the analogy between gravitational fields and electromagnetic ones. But their point of view was still sort of very geocentric. They only sort of understood the fact that the Earth pulled things towards its center. They didn't really understand that things like the sun and the moon were also affected by gravity. So, for that notion, we owe it to Newton. And he's the first person to make the point that all bodies are affected by gravity in proportion to their masses. And so it's one sort of interesting thing, if you look at the original phrasing in the Principia, that was sort of his main point, right? And that the additional points that they vary as the square of the distance is actually sort of almost a kind of a footnote. But in any case, the idea that gravity affects all bodies sort of not only explains sort of apples falling on Earth, right, but it also explains the motion of the Earth around the sun, the moon around the Earth, and even how sort of the tides are affected by the gravity of the moon. And this equation obviously has been good enough to sort of put men on the moon. And so we're not really wanting for a description of gravity. Where things sort of get very interesting is sort of an explanation of the cause of gravity. So to the Greeks, it was really quite simple. If you look at Aristotle, he says that it's just the tendency of fire to move upwards, and it's the tendency of earth to move downwards. As he says, all earthy things move towards the center of the earth. And the rate at which they're going to move towards the earth just depends on the proportion that they're composed of the four elements: earth, air, water, and fire. And so, you arrive by this sort of thinking at the idea that heavy things should be accelerated towards the earth, at a greater rate than light things. So it's kind of surprising to us, but this idea sort of holds sway for sort of 2,000 years until it's sort of blown apart by Galileo, sort of who proves that the acceleration felt by large objects is exactly the same as the accelerations felt by small objects. And so then again, the question of what causes gravity sort of becomes sort of wide open. So it's interesting to see that Newton, he says, for the cause of gravity is what I do not pretend to know. And this was 5 years after he had published, his Principia and his universal law of gravitation. So we have this idea then that sort of in the 21st century, thanks to Einstein, we're sort of much, much better off. Sort of the popular explanation then is that there is actually no such thing as gravity. It's just an impression that we get due to the fact that space is curved. Or put sort of more simply, mass tells space-time how to bend, and space tells mass how to move. The very interesting thing is that Einstein himself never actually said this, and by all sort of evidence, he didn't believe it himself. This sort of popularization of the idea comes from one of his intellectual heirs, John Wheeler, who was no slouch himself. He's the person who coined the term black hole. But it's interesting if we look at what Einstein himself said about gravity. He had actually a very, very different view. So sort of in the original publication of the theory of general relativity, he's very emphatic that you cannot replace an arbitrary gravitational field by a state of motion of the system. And he says, of course, to say that it's, a very sort of self-evident proposition. And even later, when he wrote about it sort of in 1921, which is a year before he won his Nobel Prize, he was careful to say that, a gravitational field cannot be done away with by any choice of coordinates in a finite region. The point then is that for Einstein, gravity wasn't the curvature of space-time. The fact that space-time curved was a manifestation of gravity. So in a sense, this doesn't really do away with the problem of what is gravity. The question still remains, what is causing space-time to bend? What is gravity? So to my hit list of thinkers on gravity, like we have a new one, which is Eric Verlinde. And he proposes that gravity is actually a thermodynamic process caused by entropy. And he sets up this idea then in opposition to another sort of equally compelling hypothesis that gravity is caused by a particle called the graviton. So the idea that gravity is caused by a particle is an attempt to sort of fit it into the paradigm of the Standard Model, right? So by the Standard Model, we have four fundamental forces, right? We have the strong force that holds nuclei together, right? We have the weak force that causes radioactivity and fission. We have an electromagnetic force which holds sort of charged particles together, such as the proton, the electron. And then, hopefully we also have a gravitational force which belongs to this set. So the main sort of model, the operational theory then, is that when you have two particles that are influenced by a force, let's say two protons that are moving away, it's not action at a distance. There's actually some other particle sort of mediating this process. And sort of analogy might be sort of two basketball players passing a basketball between them, and the impulse of receiving the basketball sort of moves them further away, causes them to sort of feel a force. So in the case, let's say, of electromagnetism, the particle that we're sort of most familiar is the photon. And then there's the hope that gravity operates under the same principle and is mediated by a graviton. The problem is that when you look at this more closely, the idea starts to present a few anomalies. So one small problem is that the force of gravity is much, much smaller than any of the other forces, right? So the electromagnetic force is sort of 100th time smaller than the strong force, but it's roughly 10 to the 40 times larger than the gravitational force. So the gravitational force is not just a billion times weaker, it's a billionth of a billionth of a billionth of a billionth times weaker than the electromagnetic force. So one of the consequences of this is that even if gravity is caused by a graviton, what are our realistic chances of ever detecting this particle? So Freeman J. Dyson has actually sort of done this calculation, and he says, okay, what's the biggest mass close to the Earth? It's the sun. So let's calculate, assuming that gravitons exist, how many gravitons is the sun emitting towards the Earth? And he calculates that it's sort of 10 to the 24 gravitons per second. So that's actually more gravitons than there are seconds in the entire history of the universe. But even then, just because the force of gravity is so weak, even if you had a detector the size of the Earth with the same mass and diameter, sort of in the 5 billion years we have left before the sun sort of explodes, you'd probably expect only to detect 4 gravitons, right? So you'd only probably be able to detect less than 1 graviton every billion years. So our prospects of detecting a graviton, at least directly, are sort of very, 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 very dim. And that leaves us a lot of room to sort of speculate. And so one of the recent ideas, which I put on my hit list, right, comes from Verlinde, and this was cited when he won the Spinoza Prize, that maybe we're making a category error, in the sense that maybe gravity is not a fundamental force in the sense of the other forces in the standard model, right? Maybe it's a thermodynamic force, right? Maybe it's what he calls an entropic force. So what is an entropic force, right? Well, a very nice example of an entropic force is osmosis, right? So if we were to fill a vessel with sort of fresh water and salty water and put a semi-permeable membrane between them, something very odd would happen, which is that the clear water would actually force itself into the chamber with the salty water and push it upwards, right? This is a force that appears because of an increase in entropy. So what is entropy, right? Here I've illustrated with my jelly beans. Entropy is sort of a state of maximum disorder. And it sort of happens sort of naturally. Nature tends to prefer states of high entropy. So just as we have these colored jelly beans over here, right? It's natural then for the fresh water to want to mix with the salt particles. And when it does that, right, it creates a force and releases a lot of energy. And it's actually a very, very considerable force. So if you were actually to do this experiment and fill a chamber with salt water and fresh water, right, you would have enough energy, you'd have a strong enough force, right, to push your salt water chamber 30 meters into the air, right? And so that's sort of the equivalent of 30 atmospheres of pressure. So entropic forces are actually very, very, very powerful. So Verlinde's idea then is that what if gravity is actually an entropic force, right? So it's just a force that's unleashed every time a system tries to increase its entropy, right? So if we're just looking at the surface of the Earth, you can imagine a mass sort of approaching it, right? And the entropy of the surface sort of increases. And just as when we were increasing the entropy of our salty part of our vessel, we experience this enormous force, right? If we were to have this change in entropy at the surface, right, we're also going to feel another force. And Belinda says, okay, maybe that force is the force of gravity. So we can find a nice system to test this. I spoke a little bit earlier about black holes. So black hole is a region where the force of gravity is so strong that not even light can escape. And what's nice is that they're even more massive than the sun, right? They usually occur from collapsed stars. So thanks to Stephen Hawking's, we know that the entropy of a black hole is all on its surface. And we also know its temperature. So if we have a reasonable guess for how entropy changes as matter approaches the hole, right, we can use our equation to show temperature times the rate of change of entropy to calculate what the force was. So Belinda, he noticed that when you do this sum, use the temperature of a black hole and you multiply it by the rate of entropy, lo and behold, right, you recover a force that's exactly the same as Newton's law of universal gravitation. So in other words, he's able to show that actually considering this as an entropic process gives you exactly the same force as the force of gravity. But this kind of has some nice consequences, right? The first thing is that we don't have to worry about the existence of gravitons, right? And it also turns out we don't have to worry about the existence of dark matter. So one way that we infer the existence of dark matter is by looking at galactic rotation curves. So here's the rate at which sort of our own galaxy, the Milky Way, rotates. And we sort of expect by Newton's law that it's going to rotate at a top speed of 50 kilometers per second. But when we actually measure it, its rotation speed turns out to be something more like 100 kilometers per second. And ordinarily we'd expect that it spin so fast that it would spin apart like the clothes in a dryer. So from this, people infer that there must be some extra mass holding it together. And so we assume that extra mass is dark matter, right? Because by Newton's law, the only source of a force, would have to be m, right? Some hidden mass. So what's nice is that by Belinda's theory, right, we actually don't have to have an extra source of matter, right? We just can assume that there must be some extra source of entropy, sort of dark entropy, or that our law of entropy scales slightly differently with distance, right, to account for this difference between our observed and expected velocity for the rotation of galaxies. So as always, when he sort of published his ideas, they were sort of popularized in the press in a way that's sort of completely misleading, but still kind of amusing. Most newspapers sort of took it to mean that, gravity doesn't exist or gravity is an illusion, kind of like this cartoon from the New York Times where somebody reads the news and sort of all of a sudden everything starts to float up in the air. But again, this is to sort of misunderstand the proposition. The proposition isn't that gravity doesn't exist. The proposition is that it's caused by entropy rather than some sort of mysterious particle. So we sort of seen that the idea works very well at sort of very, very large scales, right? What about sort of on Earth at more sort of terrestrial scales? What kind of experiments can we do to sort of test it? And one nice experiment is sort of the quantum mechanical bouncing ball, right? So the question is not what happens when you drop a basketball, but what happens when you drop a subatomic particle, like a neutron or a proton or something very, very, very small. And what's interesting is that if you were to do that, the situation is sort of very, very similar to sort of electron in the electric field of a nucleus, which is to say that you don't just find the electron in any position, right? You find it in fixed orbits at specific energies. And so if you were to drop a subatomic particle on the surface of the Earth, right, you're also going to find it not at any sort of height, but at sort of very, very specific quantized levels of energy. So George Breit was the first person to calculate this in 1928, which is just sort of 2 years after Schrödinger sort of gave us the theory by which we could calculate it. And he had to wait, unfortunately, 70 years before somebody tried this experiment, which was to sort of bounce neutrons above a sort of a flat surface and sort of measure the heights at which they're going to appear on the detector. But lo and behold, just as theory predicts, right, your neutrons sort of appear at quantized heights above the surface. So this is sort of a win for quantum theory, right? But it's kind of a problem for entropic gravity. Classically, you don't have to really worry about the entropy of your particle that's being attracted to a large object. But quantum mechanically, you do kind of have to worry about that. And so you end up with an MC squared, which is the energy represented by the entropy of the ball itself, right? So, so quantum mechanically and experimentally, we sort of see that 0 is sort of the lowest state. But when we have entropic gravity tells us that actually the lowest state should be this amount of energy above the surface. So I'm just going to pull all my threads in together, right? So, so the Newtonian view of gravity, right, is that we have sort of a gravitational field, right, that's pulling matter in, and you can extend this to the standard model idea that this field can be quantized, and then you would expect to find some kind of intermediary particle, like a graviton, mediating the force between two masses. Verlinder's idea is that gravity at the surface of the attractive surface, right? So there's no classical field, right? And then you would expect not to see any gravitons. And you would also expect not to see any dark matter. But even without that, you're able to explain sort of a whole host of classical phenomena, like the difference between our expectation of how galaxies rotate in theory and how they rotate in reality. The only sticking point sort of comes, the reason why this hasn't become sort of a canonical theory is that when you look at terrestrial sort of situations, you kind of run into a contradiction between entropic gravity and quantum theory. So thank you. That's entropic gravity in a nutshell.
Thank you very much for your fantastic and interesting presentation. We learned a lot. We have a few questions for you. My first question is there a transition to when gravity decays from its classical nature and when it decays linearly with distance?
Yeah, so as I was sort of saying with the galactic rotation curves, in fact, that transition would be exactly the point when the curve departs from the Newtonian expectation and the sort of measured expectation. And it's sort of, in that sense, it's a theory that agrees that transition is exactly the same transition as you have in modified Newtonian dynamics, right, MOND, as well. So the answer to that question is yes.
Thank you. My second question for you is, how does MOND explain gravity on the microscopic level?
Okay, yeah. So MOND doesn't really explain gravity on the microscopic level, right? MOND is just like an empirical adjustment to Newtonian dynamics, so that it agrees with observation. So to the extent that entropic gravity actually agrees with MOND, you could say that entropic gravity is a microscopic explanation for MOND, right? You could say that what's really happening, as I said before, is that you have this change in entropy on the surface, right? And that's sort of what ends up giving you sort of the equations for the departure from sort of classical gravitation, and then the linear predictions that MOND gives you.
Thank you. I'll now pass it on to Ren.
Thank you, Sergiy. So my first question for you is, if thermodynamic processes are irreversible, but classical processes are reversible, how can gravity be entropic?
Yeah, so that's a kind of a great question. I'd say that's one of the early objections to entropic gravity. So we know that thermodynamic processes, entropic processes, are not reversible, right? You can't really sort of uncook a chicken once you've sort of cooked it. But classical processes like the orbit of the stars, right, or sorry, the orbit of the planets, right, repeat themselves every year. So how can that be? The point is that in actual fact, thermodynamic processes are reversible, right? But you have to have sort of an infinite heat bath available to you, which we ordinarily do not, right? But if we're sort of considering classical gravitational processes, right, there is a sense in which we do have an infinite heat bath, right? The scale of our energy is set by mc squared, right? But to a non-relativistic process, right, the speed of light is infinite. And so it's almost as if, at least in that sort of regime, you do have sort of an infinite heat bath available to you. I suppose the problem then comes in what happens when you're in the relativistic limit, right? And your energy mc squared is no longer infinite, right? Are these processes still reversible? And I have to admit that I don't think anybody's really looked in closely enough to this question for me to answer it.
Well, thank you very much. That was a great answer. My other question for you is, what made you decide to come to Canada for your master's and your bachelor's?
Yeah, well, yeah, I wish I could say otherwise, but it was sort of entirely an accident. I actually did most of my education in England, which is why, even though I'm Brazilian, I have this accent. But I happened to have an uncle who lived in Montreal, and he recommended that I go to McGill. The interesting thing is that before going to McGill, I'd actually spent half a year in China between high school and university. And that's kind of what encouraged me to go back to China once I had finished my studies at McGill.
That's actually quite interesting that you didn't come for like education or physics reasons. You're just, yeah, I had family.
Yeah, I have a feeling that actually that actually often happens a lot. So we actually have a really nice professor in the department, and when he explained why he came to McGill to teach, it just happened that he happened to marry a woman from Montreal. So I think it happens actually quite a lot.
Oh, I think it does, honestly. Well, thank you very much for answering my questions. And now I'm going to pass it off to Maheen.
Thank you, Ren, and thank you, Ricardo, for your wonderful presentation. The question I want to ask is, if the concept of entropic gravity could potentially resolve the quantum gravity problem, do you think that at the same time it could create more problems on the more classical level?
Yeah, so I almost want to turn your question inside out, which is I want to say that I feel that classically, at least, entropic gravity doesn't create any more problems, or it doesn't create any more problems than already exist, in the sense that it dovetails sort of very nicely with MOND, which was sort of invented to explain like discrepancies in the galactic rotation curves, I would sort of say that it solves some problems in quantum gravity, in the sense that it tells us not really to worry about gravitons, that they probably don't exist, right? It does, though, sort of create some other problems, like I showed with the quantum mechanical bouncing ball, in that there's sort of a discrepancy in what it predicts for the energy levels of subatomic particles. So yeah, so I would say with classical theory, it sort of fights to a draw. With quantum theory, it's at least sort of one down. So.
Okay, interesting. I also want to ask a follow-up question to that. Based on the research you have performed on entropic gravity, what would be your scientific predictions for its future as a theory based on what you just talked about?
Well, I feel that entropic gravity, well, to start with, is no worse than other theories that sort of explain classical phenomena and in cosmology. I think that it would sort of run into difficulties if there was sort of something to disprove it. So if sort of somebody did discover gravitons, that would kill entropic gravity in sort of one stroke. But I think that in some sense, entropic gravity's problems is that maybe it explains phenomena a little bit too nicely, and because it doesn't sort of contradict them, it's sort of it's hard to disprove, and it's sort of too hard because it doesn't make any sort of new predictions, hard to prove that it's sort of better than some of the alternative theories like MOND that are in existence.
I see. I think it will be very exciting if we do end up discovering gravitons, but thank you so much for your insightful answers. And I will now hand it over to Marianna for some final questions.
Thank you, Maheen. And that was a very nice presentation. So I do have a couple questions of my own, starting with what was the most challenging part of your research thus far?
So I don't think any part of it was like exceptionally challenging, though I would say one part of it was very, very sort of surprising, which is sort of looking closer into what Einstein thought about gravitation. I sort of, in a sense, had sort of accepted what people had told me, that the curvature of space-time was gravity, and I was surprised to see, by how much Einstein disagreed with this thought. And in some sense, his idea of what gravity was is sort of the opposite for the way that it's usually represented, not only on TV, but even in the classroom. So, people usually want to say something like, Einstein showed that gravity was only sort of apparent, and it was just, really just another form of acceleration. But reading Einstein's words, it seemed that actually he wanted to show the opposite, which is that not only that gravity was real, but non-inertial forces, the kind of forces that we feel on acceleration, were just as real as gravitational ones. So that was very interesting too.
Yeah, that is very interesting and kind of surprising, honestly. So for my second question, I would like to ask, what is your most favorite part of your research that you've done thus far?
So I think my favorite part was sort of something that sort of Sergiy sort of alluded to, right? Which is, what would sort of be a microscopic explanation for MOND. Right? So it's kind of nice when you have sort of empirical results, and then along comes a theory that can sort of explain it. So in some sense, entropic gravity sort of gives you sort of very similar classical results, like it gives you, the inverse square law, but but it does so sort of through an entirely new and different route. So I thought that was sort of very, very, very satisfying.
Yes, well, thank you again for your presentation and for answering all of my questions.
Hey, welcome.
Well, everyone, you've been listening to the Alan I. Carswell Observatory's weekly Teletube broadcast, the Astronomy and Astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Sergiy, Ren, Maheen, and myself, Marianna, with our special guest, Ricardo. Make sure to leave any comments or questions in the comment section of the video and talk to us right now in chat. We'll be around for the next 20 minutes to answer all of your questions. All of our programs are free, but if you'd like to make a donation, please see our website at yorku.ca/science/observatory. You can always connect with us on Twitter with the handle @YorkObservatory, and check out our website for show notes, content updates, and contact information at yorku.ca/science/observatory. Thanks for tuning in, clear skies, and have a good night, everyone.